Welcome back. This should be the final talk of the fine-grained complexity thread given by Yinzhan.
I'll talk about harness for click problems, mostly click detection and click listing. So a K-click is a set of K vertices where there's an edge between every pair of vertices. And it is a K-click detection and finding is a special case of subgraph detection and finding. And here we usually have a kind of large graph as input, such as the graph on the left. And we're also given a pattern, which is typically smaller, such as this 5-click on the right. And the subgraph detection problem asks us to answer whether the large graph contains a pattern as a copy. And the subgraph finding problem, in the subgraph finding version, if there's a copy, we also have to output this copy. And click, of course, is the densest graph, k-vertex, densest k-vertex graph. And also, we can formally show that if we can detect a k-click in some amount of time, and then we can also detect any other k-vertex graph in roughly the same amount of time. So in this sense, k-click detection is the hardest problem for k-node graphs. And the notion of clicks are studied at least as early as the 1940s in the context of social network cohesiveness. And it can be used to capture social relationships, such as friendships. And dense graph detections also have many applications in other areas, such as data mining, finance, and detecting a dense subgraph can be useful for finding communities in networks and so on. So click finding is an important problem. And in this talk, I will first briefly talk about finding K-clicks. And the main focus of the talk will be about listing K-clicks, and more specifically will be about listing triangles. So here's a reminder of the definition. In click detection, we are given a graph, and we have to determine whether the graph G has a click of size K. And in the click finding version, we also have to return a K-click if there is one copy. And click is actually one of the first problems to be known to be NP complete, and if one K is part of the input. So unless P equals NP, there's no efficient algorithm for K-click in the case when K is a part of the input. So we will focus on the case where K is fixed, that K is a fixed constant that is independent of N. And the brute force algorithm for K-click runs in N to the K time. Basically, we just enumerate all K tuples of vertices and check whether they form a K-click. So the question is whether we can find a K-click much faster than this N to the K brute force time. And under the exponential time hypothesis, it's known that there's no N to the little o K time algorithm for K-click finding. And the exponential time hypothesis says that no algorithm can solve CNF set on N variables in time 2 to the little of N. So it is a weaker version of the strong exponential time hypothesis we saw earlier in earlier talks. And in strong exponential time hypothesis, we are basically assuming that CNF set requires 2 to the N minus little o of N time. And here the assumed running time is much lower. So this hypothesis is weaker and more likely to be true. So under exponential time hypothesis, the best we can hope for is to find a constant alpha so that K-click finding can be solved in N to the alpha K time, hopefully for some alpha very small and less than 1. And so indeed, there is a better algorithm that can give some alpha less than 1 using fast matrix multiplication. We will use omega to denote the exponent so that 2n by n matrices can be multiplied into the omega time, which is known to be less than 2.372. Using fast matrix multiplication, K-click finding can be solved in n to the K minus 3 minus omega times K over 3 float time. And for simplicity, throughout this talk, we will make the assumption that omega is 2. And when omega is 2, this running time can be simplified to n to the k minus k over 3 float. And for a 3-click or triangle, this running time is n to the omega. And the algorithm is basically the following. We're given the adjacency matrix A of the input graph, and we use fast matrix multiplication to compute A squared. Then the UV entry of A squared will count the number of 2 passes from U to V. And then we basically enumerate all pairs of vertices U and V and check whether there's an edge between U and V and whether there's a 2 paths from U to V. And so the bottleneck of this algorithm is to compute A squared, so the running time is n to omega. For larger K, the idea is basically to first reduce K-click finding to triangle finding and then run this n to omega triangle finding algorithm. For instance, when K is 6, we first group all pairs of vertices in the input graph as a super vertex. And then between every pair of 2 super vertices, which corresponds to 4 vertices in the original graph, we will add an edge if there is a 4-click in the original graph. Then for every triple of super vertices, there is a triangle if and only if the corresponding 6 vertices in the original graph form a 6-click. So now the problem becomes finding triangles in this new graph whose number of vertices is n squared, which can be solved in n to the 2 omega time. And more generally, when k is divisible by 3 and omega is 2, the running time is n to the 2k over 3. And when k is not divisible by 3, the formula is slightly more complicated because the graph we created in the reduction will be unbalanced.
So in the previous slide, you said we get this little O of k under the exponential time hypothesis. If we assume the strong exponential time hypothesis, can we get a better bound on that quantity or not?
I don't think there's a concrete constant on the strong exponential.
Okay.
What is the best runtime for the combinatorial algorithm?
Oh, yeah, the best runtime for combinatorial algorithm is basically up to Polylog improvements.
So I think I got here the algorithm that you just described. Suppose so you are looking for a 6-click. So what you do, you partition the graph into how many parts?
It's not partition. It's like picking every pair of vertices and create a new vertex in a new graph. So the new graph will have n square vertices, and the original graph only has n vertices.
Okay.
Yeah, and in the new graph, each edge will encode whether each edge is between 2 super vertices in the new graph, which will correspond to 4 odd vertices, right? So we add an edge if among these 4 odd vertices there's a 4-click. Then a triangle in the new graph will be a 6-click in the old graph.
So I got it. I don't know.
So is this algorithm for the finding or detection?
Oh, yeah. Actually, for constant k, finding and detection are actually more or less the same problem. You can solve them in roughly the same amount of time. But when we say k-click, you can think it as a k-click finding.
Thank you.
Yeah, so that's it for k-click finding, and now I will switch to k-click listing. And now the problem is, given a graph G, we want to list all of its k-clicks. In the worst case, the graph itself can be a n-node complete graph, and in that case, it will have n to the k-clicks. And the brute force n to the k-time algorithm can also be used to list all the k-clicks. So it seems that this n to the k running time is optimal in this sense. But in many cases, the number of k-clicks will be much smaller than n to the k. And the question is, in that case, whether we can list k-clicks faster than this brute force running time. And in the extreme case, when G only has 1 k-click, then the previous k-click finding algorithm, which finds 1 k-click, can already list all the k-clicks because we only have 1 k-click in the graph, and which has running time n to the 2k over 3 under these assumptions. when the number of k-clicks is smaller, it's indeed possible to get faster algorithm. And in general, we can ask what if G has t k-clicks for some t between 1 and n to the k. And an n-vertex graph can have at most n square edges, but also in many cases, the number of edges in the graph will be smaller than n square. And in that case, we should denote the number of edges in the graph by m, and m will actually be the input size of the problem or the database size. So a running time in terms of m is also very natural and interesting. So suppose the graph G has m edges. It's known that G can have at most m to the k/2 k-clicks. And we can also list all these k-clicks in m to the k/2 time. Similar to the dense case, this running time is optimal when the number of k-clicks is actually m to the k/2, but in many cases, there are few k-clicks in the graph. And when the number of k-clicks is only 1, there's indeed a faster k-click finding algorithm on the right. On the left, it's a reminder of the running time in terms of n, which is n to the ck, where ck is k minus k/3 float. And on the right, the running time actually depends on the ck. So the k-click running time in terms of m is m to the ck/2 for k greater than 3 and 1 omega is 2, and it is m to the 4/3 for k equals 3. Okay, so yeah, so this is a picture. We'll talk about the right-hand side, which are like the brute force algorithms are optimal, and the left-hand side, which are the click finding algorithms.
Is there a threshold where k is larger than the threshold and then form becomes easier? Like if I know if k is n, I just look for missing n.
If k is n, then when k becomes, oh, I see. But in general, when k is dependent on n, the problem is NP complete. But maybe in some special cases, like what you said, when k is equals n, it's easy. But I'm not sure in general for what values of k the problem becomes easy. When k is, say like, when k is n minus c,
It becomes like vertex cover.
it becomes a vertex cover, which so when k is like n minus c, there's also polynomial time algorithm. Okay, so next I will focus on triangle listing. First, I will show you how to list all triangles in m to the 1.5 time. I think we also saw this in Monday's lectures, but I will show this algorithm purely in terms of the language of graph algorithms. And then I will show how to slightly modify this algorithm to get m to the 4/3 running time that can find one triangle. So this algorithm will first classify all vertices based on their degrees, and we'll call any vertex low degree if it has degree at most d, and we'll call a vertex high degree if it has degree greater than d. And for every edge uv, where u has low degree in the graph, we'll list all other neighbors v prime of u, and then check whether v prime is an edge. And if so, as we can see, because v and v prime are both neighbors of u, and we check that there's an edge between v and v prime, we can conclude that u v prime is indeed a triangle. And the running time for the first step, because for each edge, we are enumerating at most d other neighbors, because we make sure that u is a low degree vertex. So the running time for the first step is m times d. And after the first step, if there's some triangle in the graph that hasn't been listed, then we know that all three vertices of the triangle must all have high degree. So at this point, we can remove all the low degree vertices from the graph. And because the sum of degrees of the vertices is 2m, so the number of high degree vertices can be at most 2m over d. Then we just try all triples of high degree vertices. And therefore, the running time of this algorithm is m times d plus m over d cubed. By setting d to be square root m, the running time becomes m to the 1.5.
So is this essentially the algorithm that Tom showed us on
Yeah, it's more or less.
Yeah, probably more or less the same algorithm, but phrasing in another language. Okay. So now let me show how to slightly modify this algorithm to get a faster algorithm that can find one triangle. So the basic idea is to replace the brute force step by fast matrix multiplication. So here we are doing the same low degree, high degree classification of all the vertices, and for the for UV where U has low degree, we also do the same thing. And after this first step, if no triangle is found, that means any triangle in the graph has 3 high degree vertices. So now we can assume the graph has at most 2m over d vertices. And at this point, we run fast matrix multiplication based algorithm to find a triangle in this graph. And we know in a graph with capital N vertices, we can find a triangle in capital N to the omega time. So running time for the second step now is m over d to the omega. Overall running time is this. By setting d to be m to the omega minus 1 over omega plus 1, the running time is m to the 2 omega over omega plus 1, which is m to the 4/3 1 omega is 2.
Can you go back one slide? So when omega is not 2,
Yeah, omega is not 2, it's 2 omega over omega plus 1.
2 omega over omega plus 1.
It's 1.41 with the current value.
1.41. Only less than 1.9.
Okay, so indeed, when t is between, for other values of t, there is indeed a great algorithm that has that can be the brute force running time. And 2 of the authors are here in the audience. So the running time can be expressed in 2 ways, either in terms of n or in terms of m. In terms of n, the running time is n squared plus n times t to the 2/3. So this n squared part, because in a dense graph, we actually need to read n squared input edges. So this n squared part is actually inevitable in that sense. And the second runtime is in terms of m, which is m to the 4/3 plus m times t to the 1/3. And this m to the 4/3 time is the same as the running time to find just one triangle. So if we cannot improve the running time to find one triangle, this m to the 4/3 part is also inevitable. And in fact, we can. Okay.
So if omega is not 2, then 4/3 becomes 2 omega by omega plus 1.
Yes, that's correct.
And what is 1/3?
What was the second part?
Yes. So what did these numbers become when omega is not 2?
I'm not very sure. Does the authors know that?
It's a function of omega.
Okay.
It's not as pretty.
Yeah, and this n squared comes into omega.
Yeah.
Yeah, and we can actually show this running time is optimal. That's true. So on the three-sum hypothesis, Petrasco first showed that m to the 4/3 time is needed to list m triangles in an M-edge graph. So if we plug in t equals m in the second running time above, we get that the running time is m to the 4/3. So at least one t equals m, this upper bound is optimal under the three-sum hypothesis. And later, this is generalized to other values of t as well. So and now that we know under the three-sum hypothesis, this m times t to the 1/3 time is needed to list t triangles in an M-edge graph, and n times t to the 2/3 time is needed to list t triangles in an n-node graph. So the red parts are also.
Other question here. So if omega is not 2, these results are not affected. That's my guess.
Yes, these results,
Do not
the lower bounds do not depend on omega. Yeah. They match the upper bound in the ideal case when omega is 2.
Thank you.
And here the results are on the three-sum hypothesis, but later it's strengthened to a even more believable hypothesis, which I will talk about later. And I will actually show the proof for this result for the special case of t equals m. And this more believable hypothesis is this exact triangle hypothesis, which I believe we also briefly mentioned yesterday. And in the exact triangle problem, we are given an n-node weighted graph, and the task is to detect whether it has a triangle whose 3 edge weights sum up to 0. And we assume all the edge weights are integers bounded by a polynomial in n. And the exact triangle hypothesis says that to solve the exact triangle problem, we essentially need n cubed time, which is a brute force time. Why is it more believable than three-sum hypothesis? It's because that we can reduce both three-sum and APSP to exact triangle. And this implies that as long as one of the three-sum hypotheses or the APSP hypothesis hold, then the exact triangle hypothesis will hold. So it's possible that the three-sum hypothesis fails, but the APSP hypothesis still hold. In that case, the exact triangle hypothesis will still hold. And so it's desirable to design reductions from exact triangle, because if you know some problem is hard under the exact triangle hypothesis, you automatically get that it is hard under 2 of the 3 central hypotheses in fine-grained complexity. And there are, in fact, also problems known to be hard under all 3 of these central hypotheses, which are the matching triangle problem and the triangle collection problem. And design reductions from them will give you very believable lower bounds that hold under any of the 3 hypotheses. But in today's talk, I will only focus on exact triangle. And recall that the goal is to show that listing m triangles in a graph is hard. And the overall strategy of the proof is following. We'll reduce one exact triangle instance to O(n) instances of triangle listing. And in each of these instances, we will have n nodes, and the max degree of each of the instances will be square root n. So the number of edges in each instance will be close n to 1.5. And then assume, for the sake of contradiction, that if there's a faster than m to the 4/3 time algorithm for each instance, then we will get a faster than n cube algorithm for exact triangle. So this, of course, we also need that the reduction itself is efficient, but we'll see that the reduction itself is is certainly subcubic. And in fact, I will first show a slight variant of the triangle listing problem. So here, at first, we'll show that listing O(1) triangles for each edge is hard. So overall, we still list OM triangles, but now, previously it's okay to list many triangles for some edges, but no triangles for some other edges. But now we first require that we list O(1) triangles for each edge. You can think of this O(1) as something like 100, and then if some edge is in at most 100 triangles, then we need to list all of them. And if it's in more than 100 triangles, it's okay to list any subset of 100 triangles. And we can assume the input graph for exact triangle is tripartite. We can do this by just copying the graph 3 times. And between every pair of copies, we add back all the original edges with the original edge weights. And each triangle in the old graph will still present in this new graph, actually 6 times. And we also assume the edge weights are from some finite field Fp for some sufficiently large prime P. We can just take this P to be, for instance, 3 times greater than the max absolute value of the input edge weights. And doing this, and mod all the edge weights by P. And doing this will not change the set of zero-weight triangles in the input graph. So we will first split the finite field FP to square root n contiguous ranges L1, L2 up to L square root n, and each range will have size roughly P over square root n. And the basic idea is to enumerate triples of these ranges Li, Lj, Lk, and only consider triangles ABC such that the weight of AB is in Li, the weight of BC is in Lj, and the weight of CA is in Lk. And after we enumerate all possible triples of IJK, like any triangle will be included in one of these enumerations. And one of the key observations is that if it's not possible to take one number from each range that can sum up to 0, then we do not need to consider this triple of ranges. So we only need to consider Li, Lj, Lk if 0 is in the sum set of Li, Lj, and Lk. Sum set just means the sum set of two sets is just a set that can be formed by taking the sum of one number from the first set and one number from the second set. And because of this observation, we only need to enumerate all n such triples. To see this, we can just say like the sum set of Li and Lj, because Li and Lj themselves are two ranges, their sum set will also be a range, but probably slightly larger size. And in order for 0 to be included in Li plus Lj plus Lk, negative Lk need to intersect with Li plus Lj. But now Li plus Lj is a range of similar size, and we split the whole finite field to square root n ranges. There will only be O1 such ranges Lk, so that negative Lk intersect with Li plus Lj. And the main difficulty is that the edge weights are not evenly distributed. Remember that the goal is to create ON instances of triangle listing so that each instance have roughly n to 1.5 edges. But if the edge weights are not evenly distributed, then it's possible that for some triple of ranges, we include more edges, but for some other triples, we include fewer edges. That's not desirable. And also in the triangle listing instances, we will actually drop all the edge weights and let the algorithm list triangles in the graph. So it's possible that the algorithm keeps listing triangles that are actually not exact triangles in the original instance. And if the edge weights are worst case, then it's possible that we are keeping listing false positives and will never reach the actual zero weight triangle. So to resolve this, we will randomize the weights in the following way. We pick random element x from Fp, and for every vertex u, we will pick a random element yu, and then we'll create the new weights w prime in the following way. So even though the graph itself is not directed, in this step it's helpful to direct edges from A to C, from C to B, and from B to A. And for an edge directing from some vertex u to some vertex v, the new weight will be x times its old weight minus yu and plus yv. Right, so here, an edge from A to C has new weight x times WAC minus YA plus YC. Okay. And because we are directing the edges in this clockwise way, the new weight of a triangle will be x times its old weight. And because we are in a finite field, and if x is non-zero, then the set of zero-weight triangles in the graph will not change. And the probability that x is 0 is very small, so we can more or less ignore that case. So once we have these new weights, we can create the subgraphs. So as planned, we enumerate triples of ranges Li, Lj, Lk. And for each triple, we create a graph Gij, for which for edges between part A and part C, we include it only if it's in the range LK. For address between part A and B, we include it if it's in range Li. For address between B and C, we include it if it's in range Lj. And because our goal is to get a graph whose max degree is order of square root n, we also have to delete all the vertices whose degree is larger. So here we create a graph G prime ijk, which is just G prime, which is just G ijk, but we will remove all vertices whose degrees are larger than 200 square root n plus 200. And finally, once we have this G prime ijk, we will run the triangle listing algorithm to list all one triangles for each edge. And for each listed triangle, we'll actually check in the original graph whether it has zero weight. Okay, so because G ijk and G prime ijk do not have weights anymore. Any questions? So that's the reduction. So now let me show you why it is correct. There are basically two bad cases. The first one is that we can potentially delete a zero-weight triangle. And because by the way we create the graph Gij, it's always guaranteed that one zero-weight triangle will be included in one of the graphs Gij. However, in G prime ijk, we are removing some vertices with large degree. So at that step, we can potentially delete a zero-weight triangle.
Could you please remind us what is the probability solution here? What are we taking probability over?
The probability is from the random choices of x and y.
Thanks.
So and we'll show that this will not happen with a very high probability. So let ABC be any of the zero-weight triangle in the input graph. And for any B prime that's not B, the new weight W prime AB prime by definition is x times its odd weight minus YB prime plus YA. So notice that this YB prime is a fresh random variable. It's completely independent with the fact that ABC is in the graph Gij. So the new weight W prime AB prime is completely random. So the probability that it's in the range Lj is roughly 1 over square root n, because we have square root n ranges of roughly the same sizes. Therefore, by summing over all the B prime, the expected number of neighbors of vertex A in part B is at most square root n plus 1. And this square root n comes from the sum of all these B primes, and this plus 1 comes from the vertex B itself. And similarly, the expected number of neighbors of A in part C can also be upper bounded by square root n plus 1. So the expected degree of A is 2 times square root n plus 2 at most. And recall that we'll delete a vertex A only if its degree is greater than 200 times square root n plus 200, which is 100 times more than this expectation. And by Markov's inequality, this will happen with probability less than 0.01. And we can do the same analysis for vertex B and C, and therefore, we will not delete any of A, B, C with probability greater than 0.97.
So I'm confused about when taking the probabilities, since the definition of Gij involves the random choice of weights, then what does it mean to consider a probability over that?
We'll consider this as the probability that W prime AB prime is in the same range as WAB.
Just about the statement of the claim, like, is the claim for each ijk, if it has a zero triangle, then with probability?
Yeah, for each fixed. Yeah, the statement is not very formal, but basically we want to say that for each fixed zero triangle ABC, it's going to be in some GIJK.
Which depends on the random
Which
choice.
depends on random choice, but we will not delete it with property 0.79. And as you can see in this analysis, we are using the fact that YB prime is completely independent of the fact that ABC is in GIJK.
So is the claim that every triangle has a large probability of not being removed?
Yes. To say it more formally, it should be that for any zero triangle ABC in the graph, we will not delete it when we are creating this G prime IJK.
Okay.
So the second bad case is the following. So it's possible that ABC still exists in G prime IJK, but there are also many other triangles exist in G prime IJK involving edge AB. Right, so listing all one triangles for edge AB does not necessarily list this zero-weight triangle ABC. It can list all these other triangles that do not have zero weights. These are the false positives. We only need to show that this case happens with a small probability. And so let's C prime be a vertex so that ABC prime is not a zero-weight triangle. And let's bound the probability that ABC prime is in the graph GIJK. Right, so in order for ABC prime to be in the same subgraph GIJK with ABC, we must have that the difference. We must have that W prime AC and W prime AC prime must be in the same range. And in order for them to be in the same range, their differences must be between negative P over square root n and P over square root m, because this is roughly the size of each range. And the same thing holds for W prime BC minus W prime BC prime. And with some calculation, we can show that these two values are actually independent uniform random variables from FP. So the probability that both of these containment happen is at most order of 1 over n. So the expected number of such C prime is only order of 1. And as long as we are listing more than 100 times this expectation, because in that case, the number of such C prime, the probability that the number of C prime actually reaches 100 times its expectation is only 0.01. And if we are, as long as we are listing more than that, we will reach the actual C with probability 0.99. Any questions? That concludes this proof to the listing all one triangles for each edge case.
Actually, can we zoom back a little bit? Can you please remind us how we got into probabilities? I thought the statement that we were trying to prove was not really probabilistic.
The statement we are trying to prove. For this, we are saying the conditional lower bound jumping overall. Which of the statements you are referring to?
Actually, could you please remind us what was the final goal here that we are trying to prove? Sorry, I lost track of it. It's the end of the day.
It's a lower bound.
Yeah, so the final goal, back here. We want to reduce one exact triangle instance to many instances of triangle listing, and that will help us to show a conditional lower bound of triangle listing based on the exact triangle hypothesis.
Yeah, so this statement is not, there is no mention of probability here. It is like a concrete statement.
Yes. In function complexity, usually the hypotheses are defined even for randomized algorithms. So it's like even for randomized algorithms, you can solve exact triangle in faster than cube time. So the reduction can be randomized.
I see. Okay, I'm gonna make this better. Sometimes I don't mind it around that. But thank you.
Yeah, so the randomization comes from that the reduction itself is randomized. Yeah, it's okay in the context of fine-grained complexity. Yeah, so that like because we resolved two bad cases, so that concludes the proof that listing O1 triangles for each edge is hard. And finally, we want to actually show hardness of the original problem. The hardness of the problem of listing O triangles in an unmatched graph with OM triangles is hard. So to do so, we just need this lemma, which says that if we can list O triangles in an unmatched graph with OM triangles in Tm time, then we can list O1 triangles for each edge in roughly also Tm time. And because previously we showed hardness for the second problem here, with this lemma, it will imply the hardness for the first problem as well. And to show this lemma, the big sick proof idea is the following. Similar as before, we can assume the graph is tripartite by copying the vertices 3 times. And then we only need, we can also assume that we only need to list triangles for edges between part A and part B. This is because between, we are copying the graph 3 times, and between each copy, we are putting a copy of the original edges. And then for S from log n all the way down to 0, we create a subgraph GS by keeping every vertex C in C with probability 2 to the negative S. So initially, we keep every vertex with probability 1 over n. And then in each iteration, we will double this probability. And in the final round, we will keep every vertex in C with probability 1. So in the final round, all vertices in the part C will remain. Then we list all triangles in GS. And if the number of triangles in GS is not too much larger than n, we can use an algorithm that runs in Tm time to solve it. And after this iteration, if we have already listed enough edges between part A and B, then we will delete this edge in future iterations. So we have listed enough edges, enough triangles for this edge. We do not need to consider this edge anymore. And the key property we need is that each GS contains roughly m triangles. If GS contains more than much more than m triangles, we cannot use an algorithm for listing m triangles to solve it. And the correctness follows from the last iteration, right? In the last iteration, we are keeping all the vertices in C. So if at that point we haven't listed enough triangles for some edge AB, that would mean that in the final iteration, this edge AB will also be kept in the graph G0. So at that point, we will just list all the triangles the edge AB is contained in. So how do we show that GS contains roughly m triangles? And that is because for every edge that is in much more than 2 to the s triangles, it's likely that we have listed enough triangles for it in a previous iteration. So suppose some edge AB is in 2 to the s times log m triangles. Then in the previous iteration, we are keeping every vertex with probability 2 to the probability 2 over 2 to the s. Probability 1 over 2 times 2 to the s. And at that point, for each triangle edge AB is in, we keep the third vertex C with probability 1 over 2 times 2 to the s. So because AB is in more than 2 to the s times log n triangles, we expect to see log n triangles remaining that contains edge AB. Okay. And log m is greater than 0.1. So in this previous iteration, we should have listed enough triangle for edge AB with high probability. And therefore, we can assume that in iteration S, all edges that are in much more than 2 to the S triangles are deleted already. And for all other edges, we should have, for other edges that has less than 2 to the S times log M triangles, in expectation, we only expect to see log M triangles containing it in this iteration. So summing over all these edges, the number of triangles overall in this graph should be in the order of M times log M, which is still roughly M. Any questions about this reduction?
Just to follow up with Mahmoud's question about the thing that we're conditioning on, so we are assuming there's no randomized algorithm, giving a certain runtime. So from the previous tutorials, there was strong convincing evidence that you set to these problems, right? But those were all not randomized. Yeah, I just wanted to see the evidence for this slightly stronger condition.
The question is, previous reductions are not randomized. And so, okay, so first of all, if your assumption is randomized and your reduction is deterministic, then it's even better, right? And the evidence previously for sets is that there's more algorithms solving sets much faster than 2 to the n. And that also include randomized algorithms. So the people have tried to use randomization in designing these algorithms. So if you assume that you cannot solve CNF set in much faster than 2 to the n randomized time, then all this evidence will still.
Can you de-randomize this reduction?
For this particular reduction? In general, it's a very good question which randomized.
Some heating sets, right? You want to hit, so then there might be standard ways of doing it.
I think though, and this is okay in de-randomizing, might be another polynomial overhead. like a order n or order n squared overhead if you use their right.
But on the other hand, I don't know about whether we can do it for this reduction, but there were previous reductions, like the Petrashko reduction I mentioned before. It was originally randomized, but now we have deterministic reductions by Chan. They're very nice. So it's very possible that this can also be randomized, but more work is needed. So.
About this particular reduction, I'm not sure whether it can be randomized just by doing the hitting sets. So finally, I will mention some extensions to this triangle listing framework. So it's natural to ask about listing KClicks for k greater than 3. And in fact, for KClick, we know that when there's only one click, we can list it in into 2k minus over 3 times. And when the number of KClicks is maximum into k, we can also do brute force to have an optimal algorithm. And in fact, for NAT, that is at least into GK, for some GK defined there, GK is k minus 1 minus 2 over k squared minus k minus 2. As long as the number of KClicks in the graph is greater than or equal to GK, there's a matching upper and lower bound. The upper bound assumes omega's 2, and the lower bound assumes this exact KClick hypothesis, and which is a natural generalization of the exact triangle hypothesis. This says that in a given weighted graph, to find a KClick whose edge weights sum up to 0 requires roughly n to the k time. And assume this, we can show that at least in the tail, there are matching upper and lower bounds. In the middle, we don't know we don't have a matching upper and lower bounds yet. This is also similar for the case of triangle listing, where recall in Petrascu's result, we know that listing m triangles in a graph requires m to the 4/3 time, but we don't know about listing one triangle in a graph under the three-sum hypothesis. There's something known under stronger hypothesis. So here it's similar. We know something when t is large enough, but not when t is smaller than this threshold. And when the running time is in terms of m, the story is similar. When t is large enough, when it's larger than some m times m to the power of hk, we have matching upper and lower bounds. But when t is smaller, we don't know the actual answer.
So in the triangle case, when you showed earlier, the AYD algorithm was using matrix multiplication to deal with the dense. Now, when let's say you have a click of size 4, the matrix multiplication doesn't apply in the obvious way anyways. So how does that work?
In the dense case, you can still use fast matrix multiplication to solve 4-click, but like as mentioned earlier, the basic idea is to reduce 4-click to triangle first.
Oh,
but not in this case. We have
find all the 4 triangles and then.
Not quite. So it's like we will have it will be a tripartite graph for triangle listing. For the first part, it will be like a copy of the original vertices. For the second part, it's similar. But for the third part, it will be pairs of original vertices.
Okay. Right. So this is what you mentioned.
So it will be a graph of size n and n squared. And on that graph, you can apply the rectangular matrix multiplication.
Yeah, so basically we break a 4-click into 2 triangles and 1 edge.
Okay.
Yes. Okay. And so far we have been expressing the running time in terms of n and m, which happens to be the number of 1 clicks and 2 clicks in the graph. So it's also natural to ask, what if we also know the number of 3 clicks triangles in the graph, which we denote by delta? And if we know that the number of triangles is small, can we design a faster algorithm to list KClicks for k greater than 3? So if we can do this, then we can follow the following framework to design faster algorithms. Initially, when we are given a graph, we run some triangle listing algorithm to list all the triangles in the graph. And then once we have the list of all the triangles, we use an algorithm to list KClicks based on the number of triangles when given a list of triangles. And if this algorithm is efficient and if the number of triangles in the graph is small, then potentially this can be more efficient than just running the algorithms that are in terms of n and m directly. And more generally, we can ask that if we know the number of L clicks in the graph, delta L, can we use it to find or list k clicks for k greater than L more efficiently in the graph? And I don't have time to cover this kind of result, but if you are interested, you can read this work, which considers exactly this type of problem. And that's all.
Can you go back one slide? And I actually have a question for Hang and Mahmoud. So how would they instance worst case of optimal? Sorry, instance I missed it end of the day. Instance optimal algorithm. How would that work on triangles? Because now you know the number of triangles that need to be reported. What would the Tetris algorithm do, or the Minesweeper algorithm?
The bound that we have for listing KClicks basically is within only log factor certificate size raised to the power of k over 2 plus output size.
So it depends on the certificate, which is not the number of triangles, which might be something else.
Yeah, but we still have an additive factor in the output. Yeah, thanks, Hank. Plus Z. So we yes. This is for triangles.
What is ATT here?
Oh, sorry, output.
Output.
The end of the day.
AT&T.
One of our customers. Yes, so C is the certificate of the problem, which in principle can be smaller, a lot smaller than or M.
Can it
So
also
that's
be
upper
bigger?
bound as a function of M and N for this for C. Side of C.
It's adaptive to the instance. So it's not a function of M and N, but a function of how the vertices interleave with each other, essentially.
So does it solve question number 3? That's my question. So delta is out, and you're saying that certificate is smaller than n?
I thought this is for KClick, not just 3 clicks.
Does your certificate depend on the number of triangles in the graph?
I don't think so.
I misunderstood question number 3.
If I may pose a question along this line, as I said in the tutorial, a set of parameters that are very natural to databases is, so in a database, when you build, let's say, the edge relation of a graph, you would have kind of a histogram information. So you would say that for this collection of vertices, the maximum degree is such and such. The next collection, maximum degree is such and such. So it's, the parameter like delta may not be very natural, but it's a different type of parameter. So from vertex number 1000 to vertex number 2000, my maximum degree is this much. And then 2000 to 3000, maximum degree is this much. So that's kind of parameterization problem is very common in database. You can build them, you can maintain them incrementally. And it'd be great to answer these questions, but under that parameter setting. Anyways, any other questions? Okay, yeah, if not, let's call it a day.
So just to let you